Yeah, makes sense. Makes sense. Yeah, I was just like wondering, yeah, about this case, but yeah.
Yeah, it's a let me just write it for a second. I mean, let's say you have a field f, and you look at a polynomial fx over f, uh, and suppose that this polynomial already splits. This means that I can write fx as alpha times x minus alpha 1 times x minus alpha n, where the alpha and alpha 1 up to alpha n are in the original field, right? That's what it means for a polynomial to split.
Mhm.
If it is a monic polynomial, then you can replace alpha by 1, because a monic polynomial, it means that when you multiply all the x's, I mean, you have x to the n with coefficient 1, right? Okay. So you see, if the polynomial splits already over f, then I can write it in this form, and where the all the coefficient, I mean all the scalars alpha and alpha 1 up to alpha n are in the original field. And then of course you can open the expression, but the expression will of course be a polynomial over the original field, simply because if all the alphas element in the field, then all the multiplications and additions, I mean all the operations you can cook from the alphas are also elements in the field. Then if K is a field containing F, then I can simply write it just as before. Okay.
Okay. Yeah. Yeah. Makes sense. Makes sense. Thank you.
And so you should really think of it as the reason that polynomials don't always split over a field is that you don't always have a root. I mean, like x squared plus 1 over the real numbers does not have a root. Right? And so to go to, I mean, to split this polynomial, I need to go to a larger field. And if I think of it as a polynomial over the complex numbers, then it will actually split as x minus I, x plus I. Okay, so the problem of splitting is that you don't have enough roots in the original field.
Okay. Yeah, this makes sense. So basically, like the use case of a splitting field is that you have a polynomial over a field and you don't have the roots in that field, so you need to extend it to have the roots.
Yes,
Okay. Yeah.
and the way, just to, I mean, to give you the intuition, I mean, the splitting fields are probably the most abstract part that we did so far. But the intuition should be fairly simple. I mean, it all follows from this case that you start with, let's say you start with FP, and you consider a prime polynomial over FP, phi x. then we showed that if we do fp x modulo this prime polynomial, fp, remember by the analogy, fp x is like the integers. I mean, polynomials over a field behave like integers in the sense that I can decompose every polynomial into a product of primes, and I have a GCD, I have long division, and so on. So, but in any case, when I divide the by the prime polynomial, I get this is the set of all remainders, right? Just like when you do z modulo n, it's like the set of all remainders modulo n, right? And so in this polynomials over a field, I divide by a prime polynomial as a set. It's the set of all remainders. Rx equals sum ai x to the I equals 0 to k, where k is strictly smaller than n, and the ai are elements in the field. And we saw that this we can call k with addition modulo phi and multiplication modulo phi is a field. And then the interesting phenomena is that when I consider polynomials over k, so of course k contains fp. It contains fp because I can always choose a remainder polynomial to be simply a constant. So if you give me some ai in fp, I can think of the ai as a polynomial with no I mean, as a constant polynomial, right? And so I have fp contained in k. This means that I can think of phi, this original polynomial, I can think of it as also a polynomial over k. But since, I mean, just as a notation issue, we already have an indeterminant with the lowercase x. So if I want to disambiguate the situation, I need to, I mean, when I talk about polynomials in k, it's better to have another notation for the indeterminant, for the variable. So I consider polynomials over k with capital X as the variable. And then I can simply think of phi as a polynomial in this setup, right? Because phi, I mean, whatever it is, phi is some sum ai x to the I, then this phi will be the same, will be sum ai, but now the variable I changed to capital X. And what we saw is that in this setup, phi suddenly has a root in k. So if it has a root, I mean, this means that it splits as x minus alpha times some other polynomial, let's call it psi. And the whole business of splitting fields is relying on this meta trick. I mean, of course, phi originally was a prime polynomial over fp. So it cannot, I mean, prime polynomials do not have any roots in the original field, because if they had a root, I mean, I could write phi x as x minus this root times some other polynomial px. But this cannot happen because phi is prime, right? It cannot be expressed as a non-trivial product of other polynomials. So I went to this construction, and I got that suddenly I have a root. But once I can find one root, I can basically repeat the same trick. The subtlety is that psi may no longer be prime polynomial over this bigger field K. So I will split it into whatever prime factors, prime decomposition it has over K. And I will take each of the factors of the prime decomposition, and I will do the same. So I will get from FP, I will get K. And then from K, I will get, let's say, K1. And I will get a finite sequence of extensions of the field. Each of them guarantees that at least I added one root to the original polynomial. And since a polynomial can only have at most n roots, I am guaranteed that this process will stop after a finite number of steps. And this is the splitting field. Is this clear? That's kind of a high-level explanation.
Yeah. For me, yeah, this helped a lot and also clarified some gaps that I didn't know I have. But yeah. Like this meta trick especially is kind of the hard thing to think of. But yeah, I think it's clear now for me.
Yeah, let me try to even further clarify by introducing a new notion that you probably saw, but we didn't talk about before. This is a definition. So let F be a field. A polynomial in two variables over F is an expression of the form now I have two variables, let's say X and Y, and I can do powers of X and multiplied by powers of Y, and all that multiplied by a coefficient. So the coefficient, I will have a double index for the coefficient which correspond to the exponent of the X and the exponent of the Y. And here, I mean, I j may run from I mean some from degree 0 you could up to degree n for some n, where the aij are simply elements in the field. So for example, over R, you could do this, we can denote as fxy. And over R, I could say fxy is 3x squared y plus 2y squared plus x. That's a polynomial in two variables, right? So this 3 is what I denote as the coefficient of a to 1. And this 2 is the coefficient that I denote as a 0, 2, because the power of x here is 0. And here the coefficient 1 is what I, in my kind of bookkeeping, I call it A10. Okay? And if you think of it, when we talked about this K, K itself as a set is a set of polynomials. And you could say that when I take K with the new indeterminate X, capital X, then what I actually do is I consider polynomials in two variables. This is kind of technically true. On the level of sets, I am considering polynomials in two variables. But the issue is that first, right? So what is kx with a capital indeterminant? It's all the expressions of the, maybe I'll just write one a typical element here. A typical element in K with capital X is let's say R0x plus R1x times capital X plus Rn x to the n, where the ri r0 up to rn are simply polynomials in simply elements in K, right? This blue box is a typical element in K with capital X. So you can think of it as polynomial. If you just change a notation, call capital X y, then it will be a polynomial in two variables. But the difference is with the way we do operations. On polynomials in two variables, so this the set of all polynomials in two variables is denoted f x y. And on f x y, we have addition and multiplication. as usual, right? I mean, how do you, let's say I had here another polynomial, g, x, y, which is maybe of the form 5x, or let's do y squared plus 5x. Then the way I do, I mean, the way I add them is just like you would imagine. I mean, I take all the monomials now, like the kind of basic building blocks of polynomials in two variables are these guys, right? So I take all the monomials in one, and I compare them to the monomials in the other. And in the case that I have monomials of the same type, I simply add the coefficients if I want to add them. So if you will add these two polynomials, you will get f plus g is 3x squared y plus 3y squared plus 6x. And similarly, you can do multiplication. Just the formula is a bit more complicated. But notice that in k capital X, the operations are not the same as the operations of addition and multiplication of polynomials in two variables, because when I add the coefficients, I mean, when I take two expressions of this form and I add them together, or I multiply them together, I need to add or multiply the coefficients, that is these r's. I need to add them according to the addition and multiplication in k. And addition and multiplication in k is a modulo phi. So this is another example of two sets that are, I mean, that seem to be one is contained in each other, but the algebraic structure is radically different. So we don't think of them as a sub algebraic structure, like sub field or sub rings, right? So that's really the whole crux of this construction, is that it's not really polynomials in two variables, because addition and multiplication are defined differently. Any more questions about this? Okay. Last time we defined the notion of equivalence relation. So for a set X, an equivalence relation is a subset R in the Cartesian product of X with itself. So you can think of it as like R is some collection of pairs. Let's say A1, B1, up to AN, BN. It doesn't have to be finite, but just for illustrations. And with the note, A equivalent to B if the pair AB is in R. This is just a more convenient way to denote it. And this subset of pairs is an equivalence relation if it satisfies one, reflexivity, that is for any x, or for any a maybe, the pair a comma a belongs to x, belongs to R, which is equivalent to say, I mean, it's the same as saying A is always equivalent to A. The second condition is called symmetry. And it says that for any A in X, for any, A and B in X, A is equivalent to B if and only if B is equivalent to A. And 3 is the transitivity, which means that for any 3 elements, A, B, and C, if A is equivalent to B and B is equivalent to C, then A is equivalent to C. And these axioms, if you think of them, it's the natural, at least the kind of minimal properties that you would expect from a framework that declares things to be equivalent, right? I mean, an element always have to be equivalent to itself. I mean, and if A is equivalent to B, also this notation is suggesting symmetry. So I would expect that B is equivalent to A. And then this transitivity, I mean, it's very natural properties to ask for. And we saw several examples, but what I want you to get is the intuition that equivalence relation, of course, so if let's say tilde is an equivalence relation on X, we denote let's say I take an element, we denote A with brackets as the set of all the set of all B in X, such that A is equivalent to B. And this is called the equivalence class of the element A. And the quotient of X by the equivalence relation is simply the set of all equivalence classes. So the intuition of this this definition is that when I take the quotient, this is quotient set. When I take the quotient, I collapse all the elements that are equivalent to each other. I collapse them to one element, to one point. And you can think of it as kind of gluing or collapsing. It's similar points of views. And we had this example. I take X to be the integers, and the equivalence relation is mod n. Let's say n is equal to 3. Then the equivalence classes I have are, I mean, I can represent them in many ways, but one canonical way to do it is to take the equivalence class of 0, the one of 1, and the one of 2. And Z modulo this equivalence relation is simply a set with 3 elements: the blue one, the purple one, and the yellow one. Okay, so I took an infinite set, the integers, and after I defined the quotient, I collapsed it into a set of 3 elements. But what is happening here in this, for example, in this integers modulo n, is that I had the operations on the original set. I had addition and multiplication, and in fact, I have induced operations on the set of equivalence classes, because so Z modulo this equivalence relation modulo n has it is called induced operations of plus and multiplication, right? Because I can take, let's say 0. Okay, 0 is trivial, but actually I could do it for any. I mean, I take A, the equivalence class of A. If I want to add to it the equivalence class of B, I simply take the equivalence class of A plus B, and that's the result. And if I want to multiply, I simply multiply the 2 representatives. Now, it's not always true that you will get induced operations on the quotient set. I mean, when you take the quotient, you glue things together, so you might destroy the properties that you had on the original set. I mean, when I define this operation on equivalence classes, what I really need to check is that this is a well-defined function. And to check that a well-defined operation, what I need to see is that if A is equivalent to A prime and B is equivalent to B prime, which of course means that the equivalence class of A is equal to the equivalence class of B, and the equivalence class of the equivalence class of A prime, and the equivalence class of B is equal to the equivalence class of B prime. If I have this situation, to have a well-defined operation of plus and multiplication, I mean, potentially I would have collision, because I have A plus B, and this is what I defined as addition of two equivalence classes. But I could also write the equivalence classes as A prime plus B prime, and it's supposed to be the same. I mean, it is the same expression, right? But by my definition, I defined addition as addition of representatives. So I do A prime plus B prime, and potentially these two things, I mean, what I need is the purple equality between the two expressions for any A and B. I mean, for any A, B, A prime and B prime that satisfy this condition, I need the purple equality. This is what it means that my operation is well defined. But from basic properties of modulus, we know that it's indeed the case, right? Because I mean, in equivalence modulo n, it is so I mean, it is satisfied because A is equivalent modulo n to B if and only if I can write A as let's say Q1 n plus R1 and so if A is equivalent to A prime, then I can write A as, let's say, Qn plus R, and A prime as Q prime n plus R prime. And to say they are equivalent, it means that R is equal to R prime. And if that's the case, then of course, when I do, I mean, when I take, of course, the same goes for B. So B is equivalent to B prime let's go. Okay, I don't want to load up too many notations, but this would be, I mean, because of the nature of this equivalence relation modulo n, we get that the operations I just defined are indeed well defined on the quotient set. So what is happening here is that, yeah.
When you tell well defined, you mean that we can take any elements from the set or from group or from the field, and something like, for example, addition will work absolutely for all the elements, right?
I mean, when I say well defined in the formal sense, what I need when I provided, I mean, when I claim that I have an operation, a binary operation on a set, it needs to be a function, right? I mean, let's put it like this, more formally. Well defined as above means that we have a function from integers, I mean, the quotient set of integers modulo this equivalence relation times itself to itself. That's what it means to have a binary operation plus. It needs to be a function, and a function for any particular input, for any fixed input, it has to have exactly one output. It cannot have two outputs. So if I give you the input A and B, this operation, we defined it as A plus B. But now I give you the same input, but I take another presentation of this input. Namely, I give you the input of A prime and B prime, where, I mean, as before, A is equivalent to A prime and B is equivalent to B prime. So this, as elements in the quotient set, or as pairs of elements in the quotient set, these two are equal, right? But the way I define the operation, I do A prime plus B prime, and then I take the equivalence class. So in other words, the way I define the operation plus it depends on, or at least I mean, the way I defined it, it depends on the particular presentation of the elements. And if I actually claim that I have a function, I need that for two different presentations of the same input, like so. I get the output I get is the same output. Okay, so well defined really means that I have an actual function.
Makes sense.
Okay. Is it clear? This is an important point, and we will use it later on. Of course. So okay. So what I'm saying here is the particular example of modulo n And you can think later of a modulo phi. It has a similar description. Is an operation. I mean, it's an equivalence relation that is particularly well behaved in the sense that the algebraic operations I had on the original set are induced on the, induced on the quotient set, which a priori for general equivalence relations does not need to happen. I mean, there is no reason. I can cook a very easily example in which I simply identify a bunch of elements in Z. Let's say you could define, let's say, a non-example. Define on Z the relation let's identify 0 and 1. 0 is identified with 1, and for any A, of course, I need to say that A is equivalent to A. Okay, and now this very simple, this is an equivalence relation. It's very easy to check. But the quotient set, Z modulo this equivalence relation, does not have any, I mean, the operations of addition and multiplication are completely destroyed, right? So in general equivalence relation, when you take the quotient set, you potentially you destroy all the additional structure, all the additional algebraic structure, and you need to be very careful in choosing the equivalence relation so that you still have induced algebraic operation on the quotient set. But this is the particularly nice property of modulo n, and in fact also of modulo phi. Okay. How about we take a break now, or if there are questions, I can take it now. Okay, so let's meet here in 10 minutes. Can we start again?
Yep.
Okay, so just to wrap up what we talked about in the first half, let's call it proposition. The integers modulo the equivalence relation of modulo n is a ring with respect to the induced binary operations of addition modulo n and multiplication modulo n. And moreover, it is isomorphic to the ring of integers modulo n. We talked about integers modulo, I mean z modulo n. Remember this in our original definition, simply the numbers 0 up to n minus 1. We talked about it as a billion group, but in fact it is a ring because you can also do multiplication. And multiplication will be associative, and it will have a neutral element being 1 and so on. It will be compatible also with addition. I mean, it will satisfy the distributive law. And this guy here is just another way to write it. I mean, because I can represent all the equivalence classes as so, right? I mean, the equivalence class of 0, the equivalence class of 1, up to the equivalence class of n minus 1. This is an exhaustive description of all possible equivalence classes when I divide by the modulo n relation. And on these equivalence classes, on this collection of equivalence classes, I have addition and multiplication. And this addition and multiplication, it defines a ring which is isomorphic to this ring. I mean, if you want to define the isomorphism, you, for example, in this direction, you simply take the equivalence class of A, and you map it to the element A. Or, I mean, of course, here you could map it to A modulo n. Okay, and this is a injective and surjective map, and it respects, I mean, it's compatible with addition and multiplication. Of course, intuitively, you can just think that I simply chose another notation for these elements. I mean, now they are equivalence classes, but the way the operations are defined is exactly the same. I mean, again, from a computer point of view, it's the same structure. Is this proposition clear? Because I want to now generalize it to polynomials. Okay, so in polynomials, I basically have the same story. So remember, we defined f is a field, and we take a polynomial. Let's change the notation because I don't assume now that the polynomial is prime. Now I can define, I mean, I can define polynomials modulo this polynomial, this f, just as I did before. I mean, I take all the remainder polynomials let's say the degree of f is n, then I take all polynomials whose degree is strictly smaller than n. And you see, I have operation of a modulo phi, sorry, modulo f, addition and multiplication. The fact that my polynomial f is not prime does not prevent me to define a modulo f arithmetic, because modulo f arithmetic only relies on long division of polynomials. So if I want I want to multiply R1 with R2, then I write I take the ordinary multiplication of the polynomials. R1 times R2. And by long division, I know that I can write it as fx times some polynomial qx plus some remainder rx. And then I define R1, R2 modulo f I simply define it to be R, this R. Okay, so I do the same as I did with integers. I do long division and I take the remainder. And this operation of multiplication and addition modulo f, this defines a ring on a ring structure on the set that we call fx modulo f. Right, on the set of all remainder polynomials. Now, alternatively, f induces an equivalence relation on the set of all polynomials. Namely, let's say alpha x is equivalent to beta x if and only if alpha is equal to beta modulo f. That is to say, if I write alpha, I do long division of alpha by f, then I get alpha equals q1 f plus r1, and beta is, let's say, q2 f plus r2. Then, I mean, alpha is equivalent to beta if and only if R is simply equal, R1 is simply equal to R2. Okay, so now once I defined an equivalence relation on all the polynomials, then I can take the quotient set. I can do fx modulo this equivalence relation that I denoted tilde f. And tilde f is the set of equivalence classes of polynomials with respect to this modulo f relation. And the same story for integers. Again, remember, the analogy for polynomials over a field is that, I mean, you can do very similar things you can do with integers. Basically, all the things that rely on long division, it can be transported to polynomials. So here, as a set, remember, it's this the set of all representatives. I mean, sorry, all equivalence classes represented by some element in the original set. Right? So here, alpha, note, alpha does not have any degree limitation. It could be of a degree bigger than the polynomial f, or smaller. But once I do long division, I mean, once I do long division of alpha by f, the remainder that I get, by definition, is always of degree smaller than f. So I could just as well, what are all the possible results of division by, I mean, long division by f? It's the same as, I mean, I take all polynomials R, whose degree is smaller than the degree of f, which we call n. Okay, so it's just another way to describe the same set, because whenever I have a polynomial of degree bigger than n, or bigger or equal than n, I can do long division, and the remainder polynomial that I get, I mean, the equivalence class of the remainder is the same as the equivalence class of the original polynomial. And of course, on fx modulo f, we have a ring structure. Defined by taking, let's say, a representative alpha, I mean, an equivalence class represented by alpha. If I want to add to it the equivalence class represented by beta, I simply do alpha plus beta, and I take the equivalence class. And if I want to do alpha equivalence class times beta equivalence class, I simply do alpha times beta, and then take equivalence class. And just as we had in the integers, we need to show, I mean, we need to show that this indeed induces a well-defined binary operation that does not depend on representatives. But basically the same proof, I mean, if you think of it, when we prove that the modulo n operation is well defined on equivalence classes of integers modulo n, what we used is long division. And so you can transport the proof to this case of polynomials, and you get that the operation is well defined. And and the summary is that fx modulo the equivalence relation induced by a polynomial is a ring, and it is isomorphic as a ring to what we denoted as fx modulo f. Right? Remember, this guy as a set, it was defined as the collection of all remainder polynomials R belongs to fx, and the degree of R is smaller than the degree of f. And here, potentially, I have a different set, but as I said above here, I can represent the quotient set as the collection of all equivalence classes of all polynomials R with degree less than the degree of f. So again, and the operation, of course, the addition, multiplication is essentially the same. I just, from a computer point of view, I get the same multiplication and addition table. Okay? Is this point clear? Great. I kind of wonder if we should go to this example, but let's try. So this is another way of using equivalence relations. And this is called the projective line. So and consider the punctured plane. I take the real numbers square, so the plane, and I remove the origin. This I call x. And define a relation on x as I take 2 points, let's say xy, and I declare that this is equivalent to x prime y prime if and only if there exists some non-zero scalar lambda such that xy is equal to lambda x prime lambda y prime. I claim that this relation, tilde, is in fact an equivalence relation. And the way to see it, I mean, first, reflexivity. Of course, you take lambda equals to 1, then x comma y is going to be equivalent to x comma y. Symmetry, I need to show that, of course, if x comma y is equivalent to x prime comma y prime, there exists some lambda non-zero such that xy is equal to lambda x prime lambda y prime. But then, since alpha is a non-zero scalar, I can invert it, and I can get that x prime y prime is equal to 1 over lambda x 1 over lambda y. So x prime y prime is equivalent to xy. Yes.
Under what assumption can we assume that lambda is invertible? Like we can only invert a lambda if it's part of a field, right?
It is, the real numbers are a field.
Okay, fair enough. Okay, sure. Yeah. My bad. Yeah, that's true. My fault.
Okay, so, and I mean, this by design, I only declare 2 points in the, so you can picture it geometrically. I will soon elaborate, but you take a point here, xy, and it is equivalent to all the points that sit on the line that passes between this point and the origin.
Yeah, that makes sense.
Okay. But by design, I only allow 2 points to be equivalent if there is a non-zero scalar, so that one is a multiple of the other. And once it's a non-zero scalar, I can take the multiplicative inverse. Okay.
Yep.
So this is a symmetry, and transitivity. Let's say I have x, y is equal to lambda x prime, lambda y prime. And furthermore, I have that x prime, y prime is equivalent to x double prime, y double prime. This means that there is some delta such that these 2 points are the same. Then, if I simply substitute instead of x prime, y prime, this delta x double prime and delta y double prime, I get that x y is equal to lambda delta lambda delta x double prime lambda delta y double prime. So if I have that x y is equivalent to x prime y prime, and I also have that x prime y prime is equivalent to x double prime y double prime, that's that means that there exists a lambda with the first equality, and there exists a delta with the second equality. then I get the third equality, which means that xy is equivalent to x double prime, y double prime. So this is transitivity, right? If I mean, if I have this and this, then I get this. Okay, is this clear? So definition, the projective line is the quotient set you take R2 minus the origin, and you mod out by this equivalence relation. And what I claim is, okay, we saw that for some equivalence relations, if you had like an algebraic structure, you have an induced algebraic structure on the quotient set. What's happening here is that on the original set, I have not an algebraic structure, but a geometric structure. And this equivalence relation induces a geometric structure on the quotient set. So how can we represent it? So to represent the quotient geometrically, remember, I mean, we can think of, I have this I mean, I start with the punctured 2D plane. And now an equivalence class of a point is the set of all points that belong to the line passing between this point and the origin. So the whole collection of purple points is now one equivalence class. And I have many of these, right? I have another line. I take just a point here. And maybe also a green one. So each of these colors is one equivalence class. How do I represent it? I can take for each line, I can take only the points whose distance from the origin is exactly 1. Then I get the circle, which would have been a good circle if I had better drawing skills. And on this circle, I actually identify two antipodal points. And so if I identify two antipodal points, you can think of the projective line as simply one half of the circle in which I identify the two ends. So I take one half of the circle because I want to have a set of representatives which with no repetition. So I take one half of the circle, let's say the upper half, and now I identify these 2 points, right? Because these 2 points are antipodal. I mean, they sit on the same line passing through the origin, so they are in the same equivalence class. But if I identify 2 points, what I get is again a circle. Maybe I can write it like this. These 2 points, let me call it infinity minus infinity, but they are, I glue them together to infinity. So the reason it is called the projective line is that what I actually did here is, you can think of it as I took the line of real numbers and I introduced another new point, which I call infinity. And this point is, I mean, it's kind of, it's in the end in the left hand and in the right hand. I mean, if you go up in the positive direction of the real numbers, and you continue as much as possible, you eventually get to infinity. But also, if you go in the negative direction, you go to minus infinity, and this is declared to be the same point. Okay, so this is a way to represent the quotient, and it is I mean, of course, if I wanted to be rigorous about, I mean, formal about what it means to have a geometry, it would take us more effort. But just on the intuitive level, you can see that the equivalence relation defined a gluing recipe, and once I do the gluing recipe, I get another geometric model. Yes.
Oh, sorry, I don't really see the link between the more algebraic notation you had before with A and B are equivalent to A prime, B prime, if only there is a delta multiplier between them, and this. I'm missing the link between the geometrical representation and what you explained before.
Oh, okay, so let's take, I mean, think of this as xy. When we declared it to be equivalent to lambda x, lambda y for any lambda that is non-zero, right?
Yep.
But what are these points, lambda x, lambda y? You take the line with a slope lambda that passes through the origin. I mean, this blue line.
Yep.
Lambda x, lambda y is some point sitting on this line.
Yep.
Okay, and all the blue points are in one equivalence class, right?
Correct. Yeah.
And the same goes for the green and the purple. So now, just like we did before with equivalence classes, I mean, of course, on the formal level, the quotient set is simply the set of all equivalence classes. But to get a better presentation of the quotient set, I would like to have unique representation, or as unique as possible representation for the equivalence classes, just like I did with, integers modulo the equivalence relation of modulo n. I wrote it as the equivalence classes of 0 up to n minus 1.
Yeah.
And I want to do the same here. So for a line, I want to represent a line with just one point. So I could take the point on the line whose distance from the origin is 1. And let's say the point that sits on the upper half of the plane. Okay, so what I get is this half circle, but I need to be slightly more careful because this point is identified with this point. Right? They sit on the same line. I mean, this is 1, 0. This is minus 1, 0. And they are indeed, take lambda equals minus 1. It shows that they are equivalent by the definition of equivalence I set, right?
Yep.
Okay, so these 2 points also need to be. So I almost got a unique representation of equivalence classes, except these 2 guys. These 2 guys I now need to identify. So I get, maybe I should have taken the lower half, and then when I identify them, I get again the circle. Okay, is this?
I think I understand the problem of having the 2 points, but it isn't the same for the purple points and the green points. They have 2 points at distance 1 from the center.
Yeah, I'm just saying. Look, you can do it in many ways, but so if I want to have a if I want to have something like I had in integers modulo n, in which I have one equivalence class, like a list of equivalence classes that does not have repetitions.
Mm-hmm.
Then I take the upper.
I see. Okay.
Yeah, I take the upper half of the circle. I could simply not take this point and take this point.
Yep.
And then I have this unique set, exhaustive set of representatives. But if you think of it geometrically, since this point is identified with this point, even if I didn't take even if I didn't take this point, the induced geometry is such that when I go in this direction and I get to this point and I kind of continue going in this direction, I start getting into this, right?
Mm-hmm. Yeah.
Okay, so this is why I guess to be consistent, you could draw it like this, and here is the new point at infinity. Yes, Carlos?
Yeah, I was just trying to abstract this to any kind of dimension. So basically, we could also say that R2 is an equivalence class of R3. So a plane inside of R3 is an equivalence class. And
a plane passing through the origin, yes.
Why does it have to pass through the origin? That's what I don't get.
Because what you will have in so I mean the projective plane I now take R3 and I remove the origin, and I declare X, Y, Z to be equivalent to lambda X, lambda Y, lambda Z. Right?
I see. The origin crashes this completely. Okay, fair enough. Is that why you do it, or I'm not following?
I mean, so, and now I have the 3D plane, and I would like to get, I mean, let's say I have a point here, X, Y, Z. This, I mean, this we didn't cover in the course, but it's typically things you see in school, that if you take just a scalar multiplication of X, Y, and Z, okay, so it's not planes. Yeah, this was my mistake. I mean, it is still lines. So if you take lambda X, lambda Y, lambda Z, this is some point on the line passing through the origin.
Oh wow, I was not expecting that. I thought this was gonna be a plane.
No. It's a line. So it's.
Can you give some intuition on why is that? Like, why it doesn't matter that you if you bump up the degree of your kind of base playground to put it on some cylinders, which in this case was F3, why do you still get lines?
So this depends on the way you define the equivalence relation, right? I mean,
I see. Fair enough.
I wanted to define the equivalence relation in the same algebraic way that I did before. But now, the way to represent the projective plane is I take, as representatives, I take the points whose distance from the origin is 1. That is the sphere.
Yeah, exactly. Yeah, that makes sense. And this was the second doubt now that you say the sphere, because now instead of having just 2 points colliding, you have an infinite amount of them, right? Like the whole border of the sphere is colliding with itself.
Yeah, but okay, so now I will take the upper half of the sphere. let's say, this upper blue half of the sphere, and I would need to identify the antipodal points. Sorry, here the antipodal points on the base of the sphere. Okay, so it's, again, you take the upper half of the sphere and you kind of glue, let's say, the red line, you glue to the pink line. But you glue it in an order. I mean, you glue this point to its antipodal point. So it's like you have this direction here and the kind of opposite direction here.
Okay, fair enough.
And what you get is again a sphere. If you think of it, you glued, I mean, all the points on so I took the upper half of the sphere, all the points which are not in the base, not in the basic base circle of the half sphere, but they have unique. I mean, they are not glued to anything.
Yeah, correct.
But if I take the base circle of the half sphere, then half of this base circle is glued to the other half.
So would that then be infinity for you?
This would be now a line of infinity.
A line of infinity, yeah, fair enough.
Yes. Okay. So,
and the last question that this makes me wonder is, so now the 0, 0, 0, so the null point, or I don't know how to say point. I mean, this is, how can I say that? The 0 is now infinity itself. Like, we don't have 0 in this equivalence class. Like,
but we didn't
anymore.
If you think of it, we didn't have 0 in the first place.
Okay, that's true. Yeah, that's completely true. Yeah, fair enough. Fair enough.
And the reason we didn't have 0 is that we cannot. I mean,
you cannot create the equivalence class.
0 would then belong to every equivalence class. Yeah. This cannot, I mean, cannot be. What will happen is that on the formal level, you will not be able to define an equivalence relation via this formula if you have the 0. You will have a violation of the axioms of equivalence relation.
Because you will have an element that is linearly independent from the rest.
Right? I mean, it will be equivalent to all other points, but if it's equivalent to all other points, then okay, you could say that it's equivalence relation, but then it's a trivial one. I mean, it's all the points equivalent to each other, and it's an uninteresting example. Okay, so we will not. I mean, we will not do a lot of projective geometry, but I think the idea of the projective planes will be useful to give you intuition on what's coming up on elliptic curves.
I have a question.
Yeah.
Considering these equivalence classes or equivalence relations, it seems that they are very much related to homomorphisms in some sort of way. Like they give rise to some sort of homomorphism, or so. My question is, what's really the difference there, or do I have a misunderstanding here?
Yeah, I think it's a different type of object. I don't see what's your intuition here.
I think didn't we have this example with the modulo operation? And
Yes.
like, and didn't we also had some homomorphisms considering that you could basically map the natural numbers onto some smaller numbers. Set of numbers, right?
Okay. I think I understand what you're trying to say. I mean, we have a homomorphism, let's say from Z to Z mod n, right?
Yeah.
This takes a number A and it sends it to A modulo n.
Mm-hmm.
Now, when I define the quotient with respect to the equivalence relation of modulo n, I also have the quotient map that takes an element and send it to the equivalence class of itself with respect to the relation.
Mm-hmm.
And we said that I have an isomorphism, let's say from integers modulo n to integers divided by the equivalence relation. So let's paint a picture like this. On one hand, I could go from integers to Z mod n by sending A to A mod n. On the other hand, I could do the quotient set, and I also have a map. This is called the quotient map. This goes to A, and I also said that there is an isomorphism, let's say from here to here. It basically takes A to the equivalence class of A, right?
Yeah, so I think, actually, I'm wondering, what is the difference between those two? Is it just some sort of notational stuff, or?
Yeah, I mean, they are, you mean these two?
Yes, exactly.
These two, that's what I was trying to say in the propositions. I mean, they are isomorphic abelian groups or rings, if you want to consider both the addition and the multiplication together. They are isomorphic. So what does it mean for two algebraic structures to be isomorphic? It means you have multiplication tables, addition tables, and they are the same up to a change of notation. Right? That's kind of the whole idea of isomorphism, is that if from a computer point of view, it doesn't matter. It just you have the same algebraic structure, but you chose different symbols to represent it.
I see. Okay.
Okay, and this is a very good example of isomorphism. I mean, we did two different constructions. I mean, they're not equal on the nose, but they're really the same for us. So
I see.
Okay, so this is what, and these two, I mean, it's not only that these two constructions in themselves, I mean, these two purple abelian groups, say, are isomorphic. It's also compatible with the quotient maps. I mean, on one hand, I could take the quotient map here. On the other hand, I could take the quotient map here. And under this isomorphism, I get the same. I mean, if I start from an element A here, I could take the modulo n and then the equivalence class of the modulo n result. And on the other hand, I could just immediately take the equivalence class of A, and I get the same result. This is it's called a commutative diagram. But I don't want to drag you into this hole too much. But all I'm saying is that under these constructions, it's not only that they are isomorphic, but also the quotients are compatible with the isomorphism. Somebody raised a hand?
I think it was me writing in the chat. I'm sorry, madam.
No, it's okay. Is this clear, Thomas?
Yeah, I mean, I think I'm just wondering what if this is. I mean, basically these equivalence classes. I mean, it's some sort of tool you introduce, but in a way, yeah, I'm wondering for what we will be using it later. So,
well, I mean, okay, I think you can take this projective line and planes as an example of a use of equivalence classes. If you want another example, kind of from a foundation of mathematics point of view, if you remember in one of the first sessions, I gave a definition of the natural numbers. Like 0 is the empty set, and 1 is the set containing the empty set as a unique element. And inductively, you define n to be whatever you had as the set n minus 1, union the set containing whatever you had as the set n minus 1. Okay, so this is a definition of the natural numbers as sets, right? And you can ask, how would I define the integers, for example? So this gives you a definition of all the natural numbers, actually natural numbers plus 0. Now let's just call it n. How would I define the integers? So what I say, I take the set X to be all pairs of natural numbers in the sense I defined above, and define an equivalence relation on X that is on pairs of natural numbers. That is, I take AB and I declare it to be equivalent to CD if and only if A plus D is equal to C plus B. You can ask, how did I define addition on the natural numbers? But to every, I mean, I can always define n plus 1 to be, you take n and you take union the set containing the set n. So you basically, by union of sets, you have addition on natural numbers. And now I declared on pairs of natural numbers AB to be equivalent to another pair CD if this relation is satisfied. But so, and you can think of AB as representing A minus B. The reason you can think of it is the way we define the equivalence relation. We said that AB is the same as CD if and only if their difference is I mean, this is basically if and only if I had a definition of subtraction, this would be the same as saying that A minus B is equal to C minus D. Right? But if I only have addition, then I use equivalence relation to kind of speak, to be able to speak about yeah. So and if I take now this modulo the equivalence relation, I simply define in the foundation of mathematics, this is simply defined to be the integers. Okay, because you have like equivalence classes, but of course you can represent A minus B in many ways. I mean, it is like I mean, you can represent a negative number. Let's say -3. It is 3 minus 4, but it's also 4 minus 5, and so on. Sorry, -1 is 3 minus 4, but also 4 minus 5, and so on.
I see. Okay, that's cool.
Okay. So, and now you define the integers, you can define the rationals. You take pairs. You define an equivalence relation on the integer, on pairs of integers. You say A comma B. I mean, you need to define a multiplication of integers. But let's say you already have addition of natural numbers, and multiplication is just defined via addition, right? So let's say I have multiplication of integers, and now I want to define rational numbers. I define an equivalence relation on this set of pairs of integers to be AB equivalent to CD if and only if A times D is equal to B times C, which is of course secretly saying that A over B is the same as C over D. But right, but if I didn't have defined division, then this would be the way to go about and the rationals is simply pairs of integers. Again, here it's like I need that B and D. It's actually pairs of integers whose second coordinate is non-zero, to be precise. And the equivalence relation is simply defined to be, I mean, the quotient set is simply defined to be the rationals. Okay, there was a question?
Thanks.
Yeah, okay. So if you want a reading recommendation, you can Google it up. But this is like I guess piano axioms. and in definition of arithmetics via set theory. This is standard way. Now you can ask, how do I define the real numbers? For the real numbers, you need what is called Dedekind. I'm not sure how to spell it. I think it's like this. Dedekind cuts. So you will take a subsets of rational numbers, and you will define an equivalence class on these subsets, and the quotient set will be real numbers. Okay, we are over time, so just last questions to have wrapping up the discussion.